All right, good morning, everybody. We are starting week number 4 today. And by the end of this week, we'll basically be about halfway through the term. And this term's a little bit longer than most of them. Don't see my normal green Excel Center background this morning because I'm working with my own computer instead of the school's because it's not working. So just dealing with the technology the best I can, and hopefully today will go smoothly. We need to get through as much of the triangle stuff as possible. We finished up the other day with isosceles and equilateral triangles, sort of beginning the classification. Anybody have a question about any of those? All right, the next part of this is another piece of the relationships that they like to find within triangles. It's another theory called the triangle mid-segment theory. Mid-segment of a triangle is a segment connecting the midpoint of two sides of the triangles. So I can enlarge this a little bit. Oops, I don't need too much. So if you look at the big triangle here, A, B, C, D and E here are actually the midpoints of those two sides that are being connected by that segment. How would I know that that's the case just from looking at the drawing? Anybody see anything on there that's kind of tip you off that you're looking at the midpoints of those two sides?
The dash marks?
Yeah, exactly. So remember, midpoint creates two, whatever it is, it's like a bisection. You're cutting something exactly in half, so you're going to get two equal parts out of it. So on this side, on this AB side, we've got these two smaller segments, AD and DB, and then on the other side, BC, you've got the same kind of thing going on with BE being equal to EC. So in the example here, that's what you would be looking at. It's this line DE here is the mid-segment line. Now the next part of this right below that says if a segment joins the midpoints of two sides of a triangle, then the segment is something in relation to the third side and some amount as long. Anybody know? That's okay. I don't expect you to. It's really critical, though, for this to be able to use this mid-segment theory in doing calculations. Can everybody see this filled in version here? I switched from the blank one to the filled in version. So this midpoint line here, this mid-segment line creates a parallel relationship with the opposite side. That base AC is going to be parallel to DE. The nice thing here about that relationship also is that mid-segment line is exactly half as long. And so if you fill in the blanks here for 1 and 2, you see the recognition that those two segments or the pieces of that triangle are parallel. And then they write this equation in two different ways. So segment DE equals 1/2 of AC. So your mid-segment line is half of the base, half of the opposite side. why would they write it this way? AC equals 2 times DE. No takers? Well, isn't that just the inverse of DE equals 1/2 AC? If you solve that equation there under number 2, the first equation, if you solve it for AC, what are you going to do? You're going to multiply both sides by 2, right? Because that's the way you get rid of that fraction. So if you're looking for measurements of these things, these are two relationships that you can count on. So if DE is 6, AC is going to be 12. If they tell you that AC is 18, DE is going to be 9. It's that 1/2 or 2 times relationship that you'll get used to working with this mid-segment theory. Questions? Anybody? Oops, wrong one. There we go. And if you look at these examples, you can have as many of these mid-segment lines as there are sides in a triangle. All pairs of parallel segments. So what segment is going to be parallel to this XY mid-segment line? Is it RS, QR, or QS? Parallel to XY.
QS.
Yeah, it's QS. So WY is going to be parallel to QR. XW is going to be parallel to RS. So before, when we only had one mid-segment line in the drawing, I was talking about the face as though that was the bottom part of what the triangle is sitting on. When you start looking at multiple mid-segment lines like these, there's not really a base anymore. It's all about what's parallel to what. So your mid-segment line is, again, this is another situation where you kind of have to blank out of your mind these other lines and focus only on the one that's going to be parallel to the mid-segment line that you got. So that's what those first two problems are all about. Then they're just going to, the rest of these are just going to check your understanding of how those equations can be worked. So you've got, in problem number 3, you've got midpoints of all 3 sides. You've got dimensions for the outside lines, the outside sides or legs of the big triangle. And the problem is to find the measurements of those mid-segment lines. How long are they? It's not sophisticated. If PQ is 40, so it says right there, PQ is 40, how much is NM or MN?
20.
20, yeah, it's just divide it in 2, exactly. And QR, let's see, do we have QR? No, we got PR, we got LN. So LN, this is where you got to turn this equation around. Here we've got LN equals 17. So QR is not half of ln, and visually you can see that ln is half of qr. So this is where you're going to multiply by 2 instead of dividing it in half. So if ln is 17, like it tells us, qr has to be 34, and mr has to also be 17. You go back to these drawings here with all these tick marks, like these first two. Shows you what's congruent. When you have this mid-segment line here at the midpoint, it's cutting every side into 2 equal parts. So, anybody have questions so far? Just had a couple other people join us. It's good. So problem number 4. It's got a little different twist to it at the end. We got to figure out what the perimeter of that large triangle is. We've got FG is 9, GH is 7, CD is 24. Okay. So they're giving us one of the sides of the large triangle. So if FG is 9, how much is DE? This side over here. It's twice as much. Remember, these mid-segment lines are half of the line that they're opposite, the side that they're opposite. So it tells you right here, FG is 9. So automatically you should realize that ED is twice that much. It's 18. So now we got 24 and we got 18. So that's 2 of the 3 sides. GH is 7, which means CE is going to be 14. So 24, 18, and 14 is going to give you the perimeter. And all they're doing is using these 2 equations right here. It's the same equation written in 2 different ways. That mid-segment line is half of the line, the side of the triangle that it's opposite. Or said the opposite way, the inverse is that long side of the big triangle is twice of its parallel mid-segment line. Questions? Anybody? Because these are this triangle mid-segment theory. This is another couple of formulas that you should get in your notes because you'll be expected to work with these. You know, and keep some of these drawings too. Like if it was me, I'm going to have one of these drawings down here in my notes somewhere also, because this allows me to see all the parallel segments, all the parts that become congruent, like QX and XR up here in problem number 1. And if you get some of these examples down, then you're going to be able to figure out the relationship and how they got them because of those 2 equations. That's all you're going to be working with here in the mid segments, with triangle mid segments. 2 equations. Questions, anybody? And the rest of this is just more of the same. Find the value of x. Okay, they're adding some algebraic expressions in here now, but the relationships still follow the pattern because the mid segment is there. So you know from the tick marks that this is the mid segment line. It's connecting, remember, it's connecting the midpoints of two sides of the triangle. So this side over here is parallel, and it is twice as long as the mid segment line. So if I'm going to try and solve that finding x here on problem number 5, two times the mid segment line is going to equal the side that it's opposite. So there's the equation. Questions on how I got that? Mid-segment line is half of this. So if I double this, it will equal that. That's why we can take that mid-segment calculation You can do it either one of these ways, however you see it. I can take that mid-segment line and multiply it by 2. Which if you look at the original example here, this is the mid-segment line. This is its parallel counterpart. So the longer side is twice the mid-segment line. That's just the inverse of the original calculation. So there's only so many things they can do with those equations, and adding some algebra to it is part of the deal. So let's take problem number 6 and see what you can do to find the value of x. I'm going to pause the recording. It'll take a couple of minutes. So I'm taking that problem. Mid-segment line is this line right here. How do I know that? Well, mid-segment lines automatically cut the sides into 2 equal parts. Well, here's a tick mark and another single tick mark. So that means those 2 pieces of that side are the same. Over here on this long side, I do the same thing. These 2 pieces are the same. So this bottom line here, excuse me, the top line of the triangle, that's twice as long as this one, because that's what the formula says. 2 times the mid segment equals the line that it's parallel to. And I'll say side. Another bracket there. That's what this calculation is right here. AC equals 2 times DE, 2 times the mid segment. DE is the mid segment. So 2 times the mid segment equals the parallel side. So the mid segment is 6x plus 31. So I need to set up an equation that multiplies that mid segment side by 2. 2 times the side, 2x, that mid-segment line, 2 times 6x plus 31 is going to equal the other, this parallel counterpart, 19x minus 36. Now it's just equation solving. And I'm doing exactly what the formula tells me to do. Now, if it's hard to understand how this relationship is true, let's try something here. It's kind of hard to draw a straight line. What if this was a parallelogram instead of a triangle? Now, do those sides look the same now? But this one that I just drew on here, I had to add it. It's the same length as this other one, right? So this side has to equal that line, which has to equal that line. The parallelogram. All I did was duplicate the triangle, just mirror image the triangle, this existing triangle, flip it over, mirror image it here. So the calculation is actually the easy part now once you got it set up. 12x plus 62 equals 19x minus 36. Divide by 7, x equals 14.
I'm glad you did it the opposite way of what I did.
What'd you do? You take half of the long one?
No, I just did my equation differently. So I did I added 36 first to the other side. Made that part of the equation first. And 12x plus 98 equals 19x.
That does not matter whatsoever.
No, it's just good to see how it worked the other way that you did it.
And the only reason I do it this way is my personal preference, which is I want to make sure I have positive variables right from the get-go. So that's usually when I have the same variable on both sides of the equation. That's my push. I want to get them where they will remain positive, because if I end up subtracting 19x here at some point, then I got a negative variable to deal with. That's the most common mistake in pretty much every math class that I've ever taught, is somebody forgets about the minus sign. So, right, if I get the variable, with a plus sign to begin with, that's one less possible error. That's the only reason I do it that way. I like to deal with the variables first, and then the opposite. Then you already know where you're going with the other terms. That's just personal preference. If the signs don't matter to you, you're not worried about the signs, you know, you can do it any way you want. I mean, you still have to isolate the variable, just all the regular stuff you learn in algebra. You know, get the variable by itself, get all your terms collected up that go together. So anybody else got questions about that one? Okay, where are we at here? All right, there's the rules. So all the rest of these are just going to be variations, especially up through problem number 9. Everything switches though at problem number 10. Let's find the measure of each missing angle. Okay, now we're not calculating. We're not using those formulas. But what are we going to use? How are we going to be able to figure out what the rest of these angles are? You know, like problem number 10, I only see 2 angles identified here, 59 degrees here and 127 degrees there. They're not even in the same triangle. So what are we going to use to figure out those missing angles? Look back at the rules here. In the theory, look at rule number 1. The mid-segment line is parallel to the line, the side of the triangle it's opposite. What do we know about parallel lines? What kind of relationships do parallel lines give us?
Same line.
Well, think about parallel lines and transversals. What are the relationships between the angles in that when we did that lesson? Look at this. Go back to your definitions. What do I got here with this combination here where this says 127 degrees and then this one says angle 2? What's the relationship of those 2 angles right there?
A linear pair.
Linear pair, right. So you calculate angle 2 as 180 minus 127. That's an easy one. Okay. Now, this is our mid-segment line, this one that's run between 5,4 and 127 and 2. So it's parallel to this one out here. So how much is angle 4? Those 2 lines are parallel. What's the relationship that can give us, say again?
I got 29 and a half.
For angle 4? Nah.
Just the midsection. Mid-segment.
We don't have any links here, Jonathan. I'm not sure how you got that, but there's nothing there to give us that.
I thought that 59 was the length of that.
No, there's a little dot there. That's the degree measurement for that angle. There's no length measurement. There's no length information here on any of these problems. This is all about measurement of the angles. And how do we measure angles? It's by degrees. That's how we came up with the measurement for angle 2. That's 127 is not the length of anything. It's 127 degrees.
I couldn't see the dot.
Yeah, it's real tiny. So if that corner angle there is 59, how much is angle 4? What's the relationship between those two angles? Maybe you need to go back and look at your notes for parallel lines and transversals. There are four possibilities here.
59.
Who said 59?
Shelna.
Say again, I can't hear it.
Shelna.
Shelna, very good. How did you know that, Shelna? That's exactly the right answer. Aren't this angle here, this 59 and angle 4, aren't those corresponding?
Yeah.
Yes.
Same relative position to these parallel lines. If this becomes your transversal, now 59 degrees and angle 4 are in the same corresponding position with each other. So because we know the definition for linear pair, we were able to figure out angle 2. Now we know that angle 4 is 59. So now we can figure out what angle 3 is, and we can use what we just figured out for angle 4 to find angle 5, because that's another linear pair. And there's no specific order that you have to go through to find any of these angle measurements. We could have started with this 59-degree angle and realized that maybe you saw that that's a corresponding relationship first. Okay, great. Run with it. But this is another example of where the stuff that you've already learned, you have to keep it handy. Anytime you start talking about parallel lines, it's going to set up relationships, corresponding, alternate interior, alternate exterior. All three of those are going to give you congruencies. The fourth one is consecutive interior. That gives you 180. Plus, you're probably going to be dealing with linear pairs. So, again, keep your notes handy. None of this stuff that we've done so far is throwaway. So then all the rest of this in this section is just a way to make that more difficult. You know, look at number 13. Here's the parallel lines, this line and this line. These are consecutive interior angles, so we're going to add those together and get 180. Problem number 12. Here's the parallel lines. Well, these are corresponding angles, so those are going to be congruent. Those definitions are going to allow you to set up the equations and find the answers that they're asking. Questions on any of that? Go back and dig out those transversal rules. Keep that stuff handy. All right, now here's another theorem. Triangle inequality theorem. Seems kind of odd to be talking about inequalities, but it's one of these calculations that we can use. So the triangle inequality theory allows us to figure out if something is even a triangle just by looking at the length of the sides. That might not make sense at first, but if you've ever tried to build anything involving triangles, you got to make sure that your lengths are correct. Otherwise, you end up with a shape that doesn't close. It's starting to look like a triangle, but it won't connect at all three corners. So this triangle inequality theory is a way to mathematically determine if you can actually create a triangle based on the lengths of the sides. It's a simple calculation. The sum of the two smaller sides must be larger than the third side. So if you look down through these calculations here, 8 plus 17 is 25. That's larger than 24. Okay, so that's a triangle. But the one with the sides 3, 3, and 7 in number 2 is not a triangle. It won't close. And it's not that the third side is equal to the sum of the other two. It has to be larger than the third side. So now we're into greater than. We're not talking about an equation anymore. We're talking about an inequality. So the two short sides, you add them together, they have to be longer. The number has to be bigger than the length of the third side. So what about number 8? Can that make a triangle with those three side dimensions? When you add the two short sides together, is it a bigger number than the third side?
Yes.
Yep, sure is. It's not a difficult calculation, guys. I don't know why you're hesitating. 7 plus 35 is 42. 42 is larger than 41. So yeah, it's a triangle. The two smaller sides added together have to be longer than the third side. And where you're going to be tested here is in this next section. How can you figure out what the range for the sides can be? So they're only giving you 2 out of the 3 sides. So there's 2 possibilities. You can have another short side to add to the 14. Right? So anything that's larger than 8, you can make a triangle with. Right? Because 9 plus 14 will give you 23. Now, what if the 14 and the 22 were the 2 short sides? How much would the third side of that triangle be in order to actually be a triangle? If these numbers here in number 9 are the 2 short sides, what do I need the third side to be? Remember, if these are the short sides added together, they have to be bigger than the third side. So what's the most the third side could be?
35.
35, exactly right. Because 14 and 22 is 36. We can't go over that. We got to be less than 36. We can't even be equal to it. It's got to be less than. So there's the range that you can come up with. Not the values for the third side. Their triangles are going to look different because the values are different. But you could have the third side be as low as 9 or as much as 35. This is one of those compound inequalities.
How did you get 9 again?
14 and 22. No, those numbers are different. 8. Okay, let me go back to that. 8 plus 14 equals 22. I need a side that's going to give me a number larger than 22.
Okay. Cool.
So for a compound, remember your compound inequalities, you got 2 and 1. This is how you would say this. If our third side is going to be greater than 8 and less than 36. The calculation is what you see over here on the on the left. This is what you should put into your notes. So our shortest side is going to be the difference between the 2 side lengths that you have. So you're going to subtract 22 minus 14 in that example number 9 gives you 8. And remember, with these inequalities, we start by reading from the variable x is greater than 8. X is greater than a, which is the difference between the 2 sides, and x is going to be less than b, which is the sum of the 2 sides. That gives you that range. If you put this on a number line, you would be with open circles between 8 and 36. So this calculation here, and you will be tested on using this calculation. Okay, so be sure you've tried some of these examples and make sure that you're following what's being done here with these ones that are filled in. Because you're going to have to do that yourself. You're going to be given some numbers like this probably and saying, okay, is this a triangle or not? Anybody have questions on the triangle inequality? The next part of this, if you had to put your angle measurements in order from smallest to largest or largest to smallest, you can do that based on the side lengths. Think back to the isosceles triangle. What do you know about 2 angles in an isosceles triangle?
They're congruent.
Yeah, they're congruent. So that's an easy thing to put in order because you know you got 2 of them already that are the same. And you can tell that because of the side lengths. Even if you don't have angle measurements, if the 2 sides of an isosceles triangle are the same, well, they will be by definition, but if you see the numbers are the same in an example, then you know the opposite sides, the opposite angles are going to be congruent. The ordering of angles works in kind of the same way. You're looking at sides and the angle that is opposite of them. So the largest angle of any triangle is always going to be opposite the longest side. And the smallest works the same way. The smallest angle is going to be opposite the smallest side. And then of course, the third side, that's what you have left. So there's two parts to this ordering angles. One is when you have the side lengths and you're looking to put the angles in order, shortest to longest, or it says here least to greatest, that would be shortest to longest. I guess, maybe not, since it's in degrees, it would be smallest to greatest, least to greatest. Or if you want to put the sides in order, then you need to know what the angle measurements are. So in this situation here, with the example here of this triangle EDF, we have two of the three angles. Clearly, the longest side is going to be EF, right? That 103 tells you that's an obtuse triangle. That's an obtuse angle. There can only be one obtuse angle in any triangle. You can't have two because then you're over 180. So you should know automatically that that is the longest and the largest angle, and the side opposite is going to be the longest side. But we're missing the third angle. How do we find the third angle? Back to the original triangle angle sum. All three angles must total 180. So 103 and 42 is 145. Take that away from 180. Angle F is then 35 degrees. So the shortest side is EB. The second shortest side is DF. That's all there is to this ordering business. Make sure that you have these relationships filled in. Questions on that? Now these inequality theorems, may sound kind of strange, but you can have sides of two different triangles. You can have two sides that are congruent, but the third side not be congruent. Well, that's because you can have different angle measurements. And so in these examples here, if this angle A in this triangle on the left is larger than angle D, then the corresponding side from that first triangle is also going to be longer than the corresponding side in the other triangle. That's what the hinge theory is about. You think about the angle that's being used for the comparison, like a hinge and a door, open, closed, open, closed. The side opposite is going to be in that same relationship, even though you're talking about two triangles. Because you can tell they're giving you some congruencies here between sides of the two triangles. BA and C and ED are congruent. AC and DF are congruent. The converse is just the opposite. You know what the side relationships are. BC is bigger than EF. Then you know that that angle A has to be larger than angle D. And that's really all there is to that. Now the next section, and we're only going to be able to scratch the surface on this today. This is where the rubber really hits the road with triangles. Congruency. Triangles with the same sides and angles. This means that all corresponding parts are congruent. Sides and angles are congruent. Everything has to be exactly alike. If you're looking at congruent triangles, you're going to be able to write what's called a congruency statement. Very important. This second section here, congruency statement, shows you two triangles, ABC and DEF. Can we tell that they're congruent from the drawings?
Yeah.
Heck yeah. That's the easy part. Side AB is congruent to ED, right? Single tick mark. BC is congruent to FE, 2 tick marks. AC is congruent to FD, 3 tick marks. And the angle measures, those little half circles in there, do the same sort of thing with the angles. The reason that there's a couple of reasons why that's important. Put those tick marks on the right pieces. Because even if you look at the first one here, AB, they're saying AB is congruent to ED. Well, that second triangle's like flipped over and rotated a little bit. So just looking at it visually, you might not be able to tell that they are congruent. So if you have the drawings with all the tick marks already identified, then it's easy to write these congruency statements. Triangle ABC is congruent to triangle DEF. That's the congruency statement for those two triangles. Now, the nice thing about having a congruency statement, you don't need the drawings anymore. And you automatically know what's congruent to what. The order is essential. So if all you're talking about are the angles, whatever's in the first position in each one of those congruency statements, those are congruent angles. Angle A is congruent to angle D. And if you look at the drawing to compare it, that's what you see. Single little half circle in A and B. B is congruent to E. 2 little half circles in the drawings. C is congruent to F. And you can absolutely rely on that. So if you had to draw those two triangles just from a congruency statement, that's how you could do that. And if you take any two of these letters together, you can create the same congruencies. You're going to identify the congruencies of the sides. And it's all by the position of the lettering. So the congruency statement tells you everything you need to know about two congruent triangles. AB, side AB is congruent to DE because that's in the first two letters of each one. Sure enough, AB is single tick mark, DE is single tick mark.